flow. The head is measured in meters. You can think of that as being the difference in elevation from the headwater to the tailwater, and the flow is measured in meters cubed per second. You can also see that we've put a few different types of turbine runners onto this graph. Let's go and have a look at each type. Here we have a horizontal Kaplan runner. The next one is a vertically orientated Kaplan runner. We're now looking at a Francis runner. And if we go up to the left here, we can see we have a Pelton runner, also referred to as a Pelton wheel. On the y-axis, that is to say the vertical axis, we start off with a head of 5, so 5 meters, and our head is gradually increasing until we get up to about 2,000 meters, and that is a significant head. If we go down, you can see we've got our flow, and that ranges from about 0.5 meters coming across, gradually increasing until we get to 1,000 meters cubed per second. And that again is quite a significant amount of flow. Notice that each one of these turbine runners has been allocated a section on the graph. This horizontal Kaplan runner operates within this section of the graph here where my mouse is going. So everything that is green up until the green dotted line as well. What that means is the horizontal Kaplan runner can operate efficiently within this range. So it's going to operate up to about 25 meters or 30 meters of head, all the way down to 5 meters of head. It's also going to operate quite comfortably within a range of about 200 meters cubed per second on the flow, going all the way down to almost 2 meters cubed per second on the flow, about 2.5, 3. So that is its operating range where it operates very efficiently. If we make the Kaplan runner vertically orientated instead of horizontal, we can see that its operating range changes as well. This time we've got an upper operating limit on the head of about 80 meters, and that's going to go all the way down to 5 meters, and we can deal with flows anywhere up to 1,000 meters cubed per second, all the way down to less than 2 meters cubed per second. And again, that is its typical operating range. Notice though that other turbine runners are not happy operating on the lower end of the graph. This particular turbine, the Pelton turbine, does not want to be operating with a low head. It simply does not work. Pelton runners operate with low flow and high heads. Francis runners operate over a very wide range, although typically they're not used for extremely high heads, but they are, however, the most versatile of the turbine runners. You can see it operates in a huge area and it can do so very effectively. As you're going to learn later in the course as well, this type of runner, the Francis runner, can actually pump water, so it can act as both a pump and a turbine. Kaplan runners operate down here. They typically operate with medium to high flows, but they are quite happy operating with also very low heads. That's what makes them quite unique. Run-of-the-river plants, tidal stream generators, tidal barrage generators, anything like that, anything that has a low head is going to utilise a Kaplan runner. You're never going to see a Pelton wheel used for anything related to run-of-the-river or for tidal generation or anything like that, simply because they use a very high head. You're going to see Pelton runners in places like Switzerland, where the terrain is very mountainous and there are sudden drops in elevation in a small area. The Pelton runner itself has a very unique shape. You can see here it has a series of buckets mounted on the outside periphery of the wheel, and we'll look at that in the next few lessons. The Francis runner, generally it will have this shape, although the actual geometry of the runner depends upon the speed and the pressures in which it operates. The Kaplan runner is very much like a normal propeller, except the blades can be varied and their angle of pitch can be changed. So that means these blades can be adjusted and they will rotate either to the right or to the left. And that is a variable pitch propeller or a control pitch propeller. And you'll see that in action, and we'll talk about it once again just to refresh your memory when we look at tidal power generation. Let's now go and have a look at each of these turbine runners in a bit more detail. We'll look at the pros and cons of each, and then we'll discuss where you're likely to see each of these types of runners and what sort of geographical features you need in order to use one of these runners within your power station. What we're looking at now is a Francis runner. See that the water comes in from the right hand side and it's delivered to the runner radially. The Francis type runner is actually a mixed flow turbine. The water is allowed to enter radially because it comes in from the sides, is drawn into the centre and then drops out of the bottom. So compared to an axial flow turbine, there's quite a lot happening. If this was an axial flow turbine, it would just flow in from the top, go straight through the runner and drop out the bottom. Not so here. We're using radial entry where we are flowing to the centre of the runner and then we are dropping out of the bottom in an axial manner. So that's why we call it mixed flow. Radial entry and axial discharge. Notice that we have quite a unique shape. The scroll case itself, sometimes called a spiral case, gets narrower as we loop back around to where the water enters the scroll case. The reason it does this is because we want to distribute the water to all areas of the runner in an even manner. But we can see the diameter of the water inlet here is very large. The diameter of the water inlet on this side gets gradually narrower as it comes around. So you can see that if we zoom out, you can see gradually narrower, but this ensures that all of the water is delivered evenly to the runner. So we're not getting a huge influx of water that just flows into the runner on one side. That would cause an imbalance, potentially vibration, which may even damage the runner. Not only that, but the runner is going to operate inefficiently. We use a wicket gate to feed the water into the runner. This is our wicket gate here. You can see that there are sort of plates that are mounted between the water suction side and the runner itself. The wicket gate is controlled hydraulically. See, we've got two hydraulic cylinders here. If one of the hydraulic cylinders, let's imagine for a moment this one where my mouse is now, if that was fully extended, then usually the other one on the lower side of the screen where my mouse is will retract. When they do this, they're actually going to turn this entire assembly here, and that is going to rotate the position of all of the wicket gate paddles. So all of these pieces here are going to rotate anywhere between 0 to 90 degrees. If the wicket gate is fully open, then the water is allowed simply just to flow through and go directly to the runner. If the wicket gate is fully closed, then none of the water is going to be allowed to flow through and get to the runner. We can use the wicket gate in an emergency to shut off the water flow, although it's more generally used for flow control. The wicket gate also allows us to angle the water as it enters the runner, and this increases the runner's overall efficiency. The upper side of the Francis runner is known as the crown, and that's where the runner vanes connect to the top of the runner. The lower side of the Francis runner is known as the band, and that's where the vanes connect to on the lower side. So let's discuss exactly what's happening here. Water is flowing in from the right and is gradually being distributed to the Francis runner as it passes through the wicket gate. As it flows into the runner, we're going to get a pressure differential created across the blades. Remember, this is a reaction type turbine, so the entire area is flooded, and this is a pressure turbine. I'm going to flow into the runner now, and you can see I'm now in the middle of the runner. If I was water, I would now drop out the middle of the runner and I would enter the draft tube. So that is the path of the water. It's relatively simple. Radial entry, axial discharge. As with all reaction turbines, we're taking the potential energy of the water and we are converting it into mechanical energy. Francis turbines are used for a wide range of applications because they're suitable for many different heads and many different pressures. This mixed flow turbine runner can pump water as well as act as a turbine, so it is essentially a hydraulic pump and a hydraulic turbine. Pump storage plants use Francis type runners. Now that we've looked at Kaplan turbines and Francis turbines, let's go and have a look at the final type of turbine, which is an impulse type turbine known as a Pelton turbine.